A property which can be interesting for beta hat is sparsity. A way to measure sparsity is to count the number of components of a vector that are exactly zero. A sparse vector, i.e. a vector with a large number of zeros, is useful for prediction purposes since it means that the prediction depends only on a small number of variables. The prediction can be computed faster and the resulting estimate is easier to interpret. So, how do we enforce sparsity? We could try to solve a penalized problem in which the penalization term corresponds to the number of components of beta which are non-zero. This is exactly the problem presented in line 21. Unfortunately, solving this problem would require to solve 2 power d optimization problems, which is computationally intractable. So we need to find a proxy to replace beta 0, and one good proxy for that is beta 1, the L1 norm of beta. To see this, look at this picture, but only on the range -1, 1. In this plot, we are only interested in f0t and f1t, which represent respectively the L0 norm, which is not actually a norm, and the L1 norm. The function f0 is non-convex. It is equal to 0 in 0 and 1 otherwise. It is quite easy to solve convex problems, so we want to transform a non-convex problem with the L0 norm into a convex problem. A common trick to do so is to replace a non-convex function by a convex relaxation of it, that is a function which is convex and such that the epigraph of the relaxation is included in the epigraph of the original function. So, in short, we started from the original problem of minimizing the data-driven term plus lambda beta 0, which was unfeasible, and we have replaced beta 0 by its convex relaxation beta 1. This is exactly the problem described in 22. In general, this problem has no closed-form solution, but it turns out that if we assume that the variables are orthonormal, then the estimate beta hat lambda 1 writes as in equation 23, which involves the positive part, or equivalently the ReLU function. Based on this expression, you see that for lambda large enough, the term in the positive part is negative, thus the positive part is equal to 0, which means that the corresponding jth component of the estimate is null. This expression proves that adding a L1 penalty enforces the sparsity of the estimate beta hat lambda 1. Depending on the strength of lambda, more or less coefficients of the estimate are equal to 0. Beware, this explicit expression holds only in the linear regression framework if you assume that variables are orthonormal.